Welcome to Kolmogorov's Axiomatic Foundation for Probability, a video lesson for probability and statistics. It might seem like the classical and frequentist views of probability are competing or are even incompatible. This contradiction isn't actually real. Andrei Kolmogorov devised an axiomatic view of probability that essentially unifies these and other approaches. It also provides us with a way of systematically organizing the outcomes of a probabilistic system into units called events, whose probabilities can be readily computed. Kolmogorov understood probability in terms of outcomes, events, and a probability measure. Outcomes are the observable states a probabilistic system can be observed in. Events are descriptive categories those outcomes might fall into. A probability measure is a means for assigning some degree of likelihood to observing the system in an outcome that belongs to one of these categories or events. We'll initially explore these concepts through some examples. The act of randomly selecting 5 cards from a standard deck of 52 playing cards is a probabilistic system. If we subscribe to the classical interpretation of probability, we compute probabilities of outcomes by counting them. There are 52 choose 5, or 2,598,960 possible ways you can draw a 5-card hand. These are the possible outcomes within this system. An event is any category that includes 0 or more of these outcomes, or 0 or more of these 5-card hands. In order to compute the probability of an event, the classical interpretation of probability instructs us to count the outcomes in the event and divide by the total number of outcomes that are possible. This defines the probability measure in this example. Drawing a full house is an example of an event. We could employ the classical interpretation of probability in order to determine that there are 13 times 12 times 4 choose 3 times 4 choose 2, or 3,744 distinct outcomes that belong to that category. That is, there are 3,744 distinct full houses possible. The probability of drawing a full house is P equals 3,744 divided by 2,598,960. Likewise, drawing a hand of nothing but red cards is an event. There would be 26 choose 5 equals 65,780 distinct outcomes that belong to that category. The probability is 65,780 divided by 2,598,960. Finally, drawing no hand at all is an event. There are 0 outcomes that belong to this category, so the probability is just P equals 0 over 2,598,960, which of course reduces to just 0. Now consider the same act of randomly selecting 5 cards from a standard deck of 52 playing cards. However, this time, let the frequentist interpretation instruct us in how to assign probabilities to these outcomes. To do this, we would need to repeatedly select 5 cards from the deck of 52, record the hand, and return the cards to the deck to reshuffle. A good question for you to consider now would be, what are the outcomes, events, and probability measure for this system? How does the system compare with the system we just analyzed? Our example so far has been pretty simplistic. However, events can be as complex as you like. If we refer to the example of 5 cards being drawn from a deck of 52, we could have also described the following categories, or events, of card hands. Drawing a hand that is a full house or consists only of red cards is an event. Drawing a hand that is a full house and consists only of red cards is an event. Drawing a hand that is a full house but includes no prime number cards is an event. Drawing a hand that has no face cards is an event. Drawing a hand that is a full house or consists only of red cards and has no face cards is an event. The use of linguistic conjunctions and modifiers such as or, and, not, and but not is what allows us to take elementary events or categories and combine them into much more complex structures. However, we must be precise and consistent in understanding what we mean when we use them. Luckily, there is an existing field of mathematics called set theory that already established the structure needed to understand and model the complex interactions that can exist between events when they are combined using these conjunctions and modifiers. So we have a parallel between probability concepts and then the set theory model. Events in the world of probability are going to be equated to sets in the world of set theory, and outcomes from probability will be equated to elements within set theory. For set theory to be a useful model for probability concepts, we need to establish a few somewhat precise definitions. This ultimately paves the road to being able to consistently model relationships between events using the or, and, not, and but not conjunctions. So a set is any well-defined, unordered collection of things in which any repetition of its elements is ignored. An element is any member of the set. If we wish to say that an object A is an element of the set capital A, we write lowercase a is an element of capital A, using the script E symbol to represent the element of relationship. If we wish to say that the object A is not an element of the set capital A, we write lowercase a is not an element of capital A, using the script E with a line through it to represent the not an element of relationship. The set which contains no elements is referred to as the empty set, and it is represented using a 0 symbol with a line through it. This definition should shed some light on why we draw parallels between events and outcomes of probability and sets and elements of set theory. Sets and elements are just abstract categories together with the objects that belong to them. That mirrors the relationship between events and outcomes that we've already seen in probability. Remember, events are essentially categories of outcomes. Categories themselves have natural hierarchical structure, subcategories within subcategories within subcategories, and so on. This is modeled by the notions of subsets and containment. We're at a point now where we can model the or, and, not, and but not relationships that we assume to exist between all events. You may have already encountered these concepts as unions, intersections, complements, and relative complements illustrated through Venn diagrams. We'll look at that, but first it's worth offering consistent semantic descriptions of these relationships between two events, A and B. So A or B is defined to be an event consisting of outcomes that belong to at least one of the events A and B. A and B is an event consisting only of the outcomes common to both A and B. Not A is an event consisting of all outcomes except those in A. And A but not B is an event consisting of all outcomes in A that do not belong to B. Shaded Venn diagrams can be conveniently used to help visualize the or, and, not, and but not relationships between events. And these are just unions, intersections, complements, and relative complements. So for instance, if we think of A or B, and recall that we could belong to that event as long as we're an outcome that belong to at least one of the events A and B, we can see why that Venn diagram has shading inside of both of the A and B circles. On the other hand, an outcome could only be a member of the A and B event if that outcome belonged to the area that was common to the A event and the B event. And that's why we only see the overlapping region between A and B shaded in the A and B diagram, or the intersection diagram. Not A, the complement of A, is the set of all outcomes that are exclusively outside of A, and so we can see why its Venn diagram is shaded accordingly. And A but not B, the relative complement, is the set of outcomes that belong to A but are excluded from B. They are on the outside of B. So that's why we are shading only the part of the A event that falls outside of the B event. Finally, we'll establish precise definitions for the fundamental set operations that we use to model the or, and, not, and but not relationships we've seen between events. So, for any two sets, A and B, the four fundamental set operations are defined as follows. Union. A union B is the set consisting of all elements in A or in B, but not exclusively. In other words, A is an element of A union B if and only if A is in the set A or A is in the set B. The union operation is both commutative and associative. Intersection, A intersect B, is the set consisting of all elements belonging to both capital A and capital B. In other words, lowercase a is an element of capital A intersect B if and only if lowercase a is an element of A and is an element of B. The intersection operation is also both commutative and associative. Complement. A complement is the set consisting of all elements that do not belong to A. In other words, lowercase a is an element of A complement if and only if lowercase a is not an element of A. Relative complement. A but not B is the set consisting of all elements of A that are not elements of B. In other words, lowercase a is an element of A but not B if and only if lowercase a is an element of the set A and it is not an element of the set B. Because of this definition, it is also correct to say that A but not B is equivalent to A and not B. These are just two different ways of representing the same compound event. To grasp how these elementary set operations work, it's really important to explore them through an example. So we imagine an internet researcher that's tracking the search behavior of members of a social network. He defines the following events. A is the event that a search has to do with a public figure. B is the event that a search has to do with current events. C is the event that a search has to do with a technical skill. The researcher is interested in several compound events and has summarized them in terms of the notation he already introduced above. A union B is the event that a search has to do with a public figure or current events. B intersect C is the event that a search has to do with current events and a technical skill. Not B, or B complement, is the event that a search is not related to current events. C but not A is the event that a search is related to a technical skill but not a public figure. Union, intersection, and relative complement are examples of binary operations. This means that they describe a relationship between two events. Complement is a unary operation that involves just one set, just one event. Under certain circumstances, relationships between more than two events can still be modeled. The simplest of these are countable unions and countable intersections. If we imagined having a sequence of events, S equals A1, A2, A3, and then on possibly indefinitely, then the countable union is just the union of all of those sets together. It's a complex looking notation, but a fairly simple concept. It consists of all of the outcomes belonging to at least one event of the sequence of the events A1, A2, A3, and so on. Similarly, the countable intersection is the intersection of all of the events A1, A2, A3, and so on. And in order to belong to the countable intersection, an outcome must belong to each and every event in the sequence. Countable unions and countable intersections are operations that make use of sequences of just unions or just intersections. However, we can establish relationships between three events or even more that make use of both unions and intersections. To do so consistently, we must assert two distributive laws. So if we let A, B, and C be sets, or if you prefer to think of them as events, that's fine, then the following distributive laws are true. The union of A with the intersection between B and C equals the union of A and B intersected with the union of A and C. Similarly, the intersection of A with the union of B and C equals the intersection of A and B paired in a union with the intersection of A and C. In general, compound mixtures of the union and intersection operator are not associative, so the use of parentheses and this axiom can help clarify your meaning, so you should really use them judiciously. We can also describe relationships between two events that involve successive applications of complements and unions, or complements and intersections. This requires us to assert the so-called De Morgan's rules. And those state that if A and B are sets, then the following statements are true. The complement of A union B is equivalent to A complement intersect B complement. And the complement of A intersect B is equivalent to A complement union B complement. With the concepts of outcomes, events, unions, intersections, complements, relative complements, the distributive laws, and De Morgan's rules in place, we are positioned to model and symbolically represent any relationship between probabilistic events that we could reasonably expect to describe in words. If we still want to precisely answer the question, what is probability, we still have a little more structure to put into place. Probability relates to measuring events. The notion of cardinality brings us a step closer to understanding what it means to measure an event. There are three types of cardinality that are of use to us, so we'll look at them conceptually first. Let's imagine a group of 13 people. This set is said to be finite because it's possible to count the members using a finite process. Imagine a clock that ticks once every second and never ceases. The set of ticks that clock will make is considered to be countably infinite because they may be counted only with the aid of an infinite process. Now imagine a dictionary of all possible words of any length that are made out of letters taken from a finite alphabet. It turns out that this set is uncountably infinite. What that means is that it would be impossible to count all of the words in the dictionary, even with the aid of an infinite process. There would be no way to associate a unique counting number with each and every word in that dictionary. In that sense, we could hatch a concept that there are strictly more words in this imaginary dictionary than anything that we could count. Before moving on, let's establish precise definitions for the different types of cardinality. So we let A be a set. The absolute value symbol applied to A represents the cardinality of A in this context. And it means the following. If A has a finite number of elements, then the number of elements in A is its cardinality. If A has infinitely many elements, but they may be placed in one-to-one correspondence with the natural or counting numbers, then we say the cardinality of A is countably infinite. If A has infinitely many elements that may not be placed in one-to-one correspondence with the natural or counting numbers, then we say that the cardinality of A is uncountably infinite. To make sense of the differences between these types of cardinality, it's helpful to have simple prototypical examples of finite, countably infinite, and uncountably infinite sets. The numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 form a finite set. We can count them using a finite terminating process. The positive integers 1, 2, 3, 4, 5, and so on form a countably infinite set. We can place them into one-to-one correspondence with the natural numbers because they are the natural numbers. Other examples include even numbers, the prime numbers, the signed integers, factors of 10, etc. Even the rational numbers, fractions, are countably infinite. The real numbers in the interval x is greater than or equal to 0 and less than or equal to 1 are an uncountably infinite set. There are certainly an infinite number of them, but they cannot be placed into one-to-one correspondence with the natural or counting numbers. Finally, we'll investigate some examples of measurements of outcomes that are finite, countable, and uncountable in nature. For example, a random system in which you attempt to guess the number your friend is thinking of 10 successive times, and you count the number of correct guesses you make, has 11 possible outcomes. You could have guessed correctly anywhere from 0 to 10 times. The cardinality of this set of possible outcomes is finite at 11. In a similar system, you might attempt to guess the number your friend is thinking of an indefinite number of times. This time, you simply keep track of how many attempts were necessary for you to guess correctly the first time. Since it will take you at least one guess, but there is no intrinsic upper bound on how many guesses you will need in order to succeed, the cardinality of this set of outcomes is countably infinite. Finally, imagine you are using a high-precision thermocouple, a kind of thermometer, to measure the surface temperature of an engine part. In principle, the thermocouple could read any positive real value between the lowest and highest temperature it can possibly register. This represents a continuum of values along the real number line, so the cardinality of this set of outcomes is uncountably infinite. We'll conclude our introduction to cardinality with the concept of a power set. It will serve a single purpose for us in probability, but it's an important one. So if x is any set, the power set generated by x, denoted p of x, is defined to be the set of all subsets of x, including the empty set and x itself. Power sets are big. When the set that generates a power set consists of a finite number of elements, we can compute the number of elements in that power set exactly, and that's the subject of the remaining theorem here. If x is a set with n elements, then the power set generated by x consists of exactly 2 to the n elements. We're finally in a position where we can state and then explore the consequences of Kolmogorov's axiomatic definitions of probability. This is where he provided a definition of a probability space in pretty general set theoretic terms. What it does for us is it gives us a consistent way of considering and comparing all of the different useful interpretations of probability. So here it is. Probability space models probabilistic systems, and it consists of 3 components: omega, s, and p. So the sample space, which we represent using the omega symbol, is the set of all possible outcomes of the natural process that's being modeled. An outcome is simply any state that the system might possibly be observed in. So that's important. Outcomes are observable states. S is a collection of subsets of omega that satisfies the properties of something that we're going to call a sigma algebra, and we're going to have to define what that is in a minute. Each subset of omega belonging to S is called an event. So subsets, categories, events, we're using those terms interchangeably. S is the collection that stores those events. Finally, the probability measure, P, is just a function that assigns a numerical value to each event E in the sigma algebra S. Now, P is going to have to satisfy 3 axioms of probability so that it assigns probabilities, the numerical values, to each event in a reasonably consistent way that causes them to behave like probabilities. Well, we've put the definition of a probability space in place, but we need to look at two parts of it in more detail. We need to know what a sigma algebra is and why it matters in reference to this set S that we collect all of our events into. And then we also need to understand what the three axioms of a probability measure are, and we'll get to that later. A sigma algebra is really a balancing act in the context of a probability space. On one hand, you don't want to choose S to be so narrow that it doesn't contain enough events to describe the situation that you're modeling. And one common pitfall would be if you had a few elementary events stored in S, and then you formed a compound event between one or two or more of those elementary events, only to find that that compound event doesn't belong to S, making it an event that you're essentially not allowed to study. On the other hand, you wouldn't want to go to the other extreme and have so many events in S that it becomes cumbersome and repetitive and unnecessary. So a sigma algebra is an attempt to impose some structure on the set of events that we're going to study that prevents the first problem at least. And so we'll see how this goes. We'll see how it accomplishes that. So we're going to let X be any set, and we're going to let S be any collection of subsets taken from X. We say that S is a sigma algebra if S satisfies the following conditions. First one is that X itself must belong to S. Well, our next property is that if we've got some event E that belongs to our sigma algebra, then that event's relative complement in X, which is really just the event's complement, must belong to the sigma algebra as well. So, upshot is that if we've got an event in the sigma algebra, the event's complement must be there too. And the third property of a sigma algebra is that if we've got some countable collection of events in the sigma algebra, E1, E2, E3, and so on, so it could be countably infinite, then the union of those events must belong to S as well. If we apply these properties to the notion of a probability space, then what they're really telling us is that our collection of events has to include the entire sample space. Any elementary event that we put into the collection of events has to be accompanied by its own complement, and this collection of events must be closed under the operation of a union. That means if you take any two or more events from the collection, form their union, that union must belong to the collection. It must belong to the sigma algebra as well. So that's what a sigma algebra is. We'll get to why it matters in a minute, but one other thing that we probably should consider is how do we make one? How do we make a sigma algebra? How do we ensure that some collection of events actually satisfies those three properties? Well, one way is through the theorem that's now on the screen. It says let X be any set. The power set generated by X is a sigma algebra. So remember, the power set of some set is just the collection of all possible subsets of that set. And so by that theorem, which we're not going to prove, any power set automatically satisfies the properties of a sigma algebra. So that might be a good place to start. Anytime we've got a sample space, we can try to construct a collection of events taken from that sample space simply by forming its power set. It's going to turn out that that's going to be a great approach to take for many of the probability spaces that we'll look at. Okay, so we know what a sigma algebra is. We know at least one way to construct one. We form the power set of some generating set, but we still haven't answered why should we care. So we use the sigma algebra as a container for organizing all of the events we hope to eventually measure using probability, using our probability measure. The reason for using a sigma algebra instead of something with a simpler structure is that the three properties provide us with just enough structure to ensure that if we selected any one or more events from the sigma algebra and formed a compound event using our fundamental operations, union, intersection, complement, and relative complement, the distributive laws and or De Morgan's laws, then the resulting event would already exist within the sigma algebra. It would be an event that's there and ready for us to assign a probability to. We wouldn't be creating something new, and this property is called closure. It's not obvious that those three properties of a sigma algebra give us this result, but it turns out that it's true. And we're just going to rely upon that truth for everything that we do going forward. If we didn't insist upon having closure in our collection of events, then we'd run the risk of creating compound events that our proposed probability measure would be incapable of measuring. Because that's the thing, we have to be able to define what our probability measure is and how it works in advance. And so if we designed it without truly knowing what all of the events are that we might want to compute the probability of, and we come along and create a new event by forming some compound event of our elementary events, then there is that risk that our probability measure would be incapable of assigning a probability to it. And that would cause the whole system to break. We call the space omega S a measurable space. This is the space consisting only of the sample space and the sigma algebra of events. And it's sort of a pre-probability space in the sense that it keeps track of all of our outcomes in events without possessing an ability to assign probabilities to any of them. We're finally in a position where we can state the three axioms of probability, show how they effectively define what a probability measure is as a part of the probability space, and then think a little bit about why they matter. So the definition begins that if we have a measurable space, sigma comma s, with a sample space sigma and a sigma algebra s, then P is a probability measure on sigma and s if the following are true. If we take any event from the sigma algebra, then P assigns a real and non-negative value to that event. Next, we have to require that P assigns a value of exactly 1 to the sample space. Ultimately, this is just a way of saying that the sample space contains all possible outcomes, and its probability must be 1, or 100%. Finally, if we have a collection of events, E1, E2, E3, and so on, that's countable and it's taken from our sigma algebra, and that they're all mutually exclusive, meaning that they share no common outcomes between any two of them. Then if you form the union of those events and assign a value to that union using the probability measure, then that value should be the same as what you would have gotten if you had assigned values to each of the individual events and then later added them together. This property is known as the special addition rule. If we take these three conditions as a unit and then compare them to what we already at least suspect to be true about probability intuitively, then they ought to seem familiar and they might even start to make sense. For instance, the first condition is just another way of saying that we don't have negative probabilities. The second condition is a way of telling us that the probability of the sample space is 100%. It reflects all possibilities that there are within the system. And the last one is just a way of saying that if you take two events that have absolutely nothing in common between them, no outcomes that are common between the two of them, then it shouldn't matter how you calculate the probability of the union of those two events, whether you take the probability of the union and do it directly, or you find the probability of the two individual events and add them together. However, the value of having Kolmogorov's axiomatic description of probability goes far beyond just confirming what we already suspected was true about probability in the first place. It gives us a firm theoretical foundation for developing some computational rules that we can use to our advantage when we're dealing with computing probabilities of compound events. So there's several rules that may be derived directly from Kolmogorov's axioms from probability, and these include the probability of a complement. So if we've got any probability space, and E is any event in that space, then the probability of the complement of E is just equal to 1 minus the probability of E. The axioms allow us to derive a formula for the probability of the empty set. So if we have a probability space, then the empty set is an event. It's the set of no outcomes, and its probability is 0. It's possible for us to derive the formula for computing the probability of a relative complement. So if we have some probability space, and A and B are any two events drawn from the sigma algebra of that space, then the probability of A but not B is just equal to the probability of A minus the probability of the intersection of A and B. We can also derive a formula for the probability of a union. This is known as the general additivity rule. So if we have a probability space, and A and B are events in the sigma algebra of that space, then the probability of the union of A and B is equal to the sum of the probabilities of A and B minus the probability of the intersection of A and B. Now, it's probably not going to be immediately obvious why any of these 4 computational rules are true. The fact remains, though, that they are true, and you can prove them. You can prove their truth, much in the same way that you would have proved any of Euclid's propositions using logic and Euclid's axioms of geometry as starting points. We're really following a similar program here for probability that Euclid would have followed for geometry. Kolmogorov's axioms are the foundational truths of probability, and we can derive all kinds of useful computational tools, such as the ones that we see here, from them just using logic. So clearly, we've just undertaken a long and abstract journey. You'll probably want to review it several times on your own. However, it's important to take note of where we've arrived. Kolmogorov's axioms of probability provide us with a consistent model for computing probabilities of events, regardless of the interpretation of probability we subscribe to. His axioms apply to all of the valid interpretations of probability. So the 4 computational rules, together and derived from Kolmogorov's axioms, make up the building blocks for actually computing probabilities of any compound event we can dream up. Finding the probability of drawing a 5-card poker hand that is a full house but does not include face cards and only involves prime numbers is no longer out of reach. More importantly, the computation of probabilities of compound events that are of much greater practical importance is also now within our grasp. That skill, however, is the subject of our next video lesson. And that brings us to the end of our look at Kolmogorov's axiomatic foundation for probability. Thanks for watching, and I hope you'll join us in the next video lesson.